Can the folks on Zoom see David's screen?
Yes.
Yeah, I can.
Awesome. Fantastic. Okay, great. So it's my pleasure today to introduce Professor David Fridovich-Keil. He is an assistant professor at UT Austin, and his research spans optimal control, dynamic game theory, learning for control, and robot safety. He's also worked on problems in distributed control, RL, active search, and currently is very focused on the role of game theory for multi-agent interactive settings such as traffic management. He is the recipient of an NSF Graduate Research Fellowship. He recently got the NSF CAREER Award, and today we have the pleasure of hearing a lecture from him about inverting games. So David, you can take it away.
Okay, thanks so much, Andrea. It's always a pleasure to talk about this stuff. I don't know, as people were kind of trickling in, Andrea and I were talking. I teach a grad course in game theory in the fall semester. So anyway, the lecture today will be kind of a bit of material that I usually teach in that course, but specialized to talk about inverting games. I understand you guys have had a lecture from another close collaborator of ours, Lasse Peters, last week that touches on solving games or formulating and solving games, I suppose. And so you can kind of view today's lecture as, maybe a continuation of that one. Okay, so the plan today is to talk about basically just make sure we're all on the same page in terms of kind of fundamentals of constrained optimization. We won't spend too much talking about this, but I want to make sure we all have kind of the correct language to discuss what we're really trying to talk about. I'll write down the inverse problem. I mean, it's not hard to write it down. And when we do it and we're, a bit pedantic about, being careful, you'll see there are some structural elements that maybe are a bit different than you may have seen. I was also joking with Andrea before the class started that, this is, I'm kind of trying to be a bit, wait, why is this not giving me a pointer? There it is. Like right here, I'm trying to be a bit, I don't know, provocative. It's not really inverse reinforcement learning that we're talking about, but it's a multi-agent version that's got, I'd say, some additional important quirks to it. And I'll kind of explain what I mean there. We'll spend a bit of time talking about solvers. I love optimization and solving optimization problems, so this is kind of where I get the most excited. And then I'll kind of close out. Maybe we'll spend a few minutes talking about some recent papers just to kind of give you a sense of how this stuff gets used in the last couple of years. And I want to basically make this really interactive. So I encourage you, please interrupt me at any point. This should be back and forth. Okay, so before we jump in to talk about constrained optimization, so can people raise your hand or otherwise indicate have you taken a convex optimization course?
We have a 0 hand raised response.
0 hand raised. Okay, this is going to be real fun, guys. So all right. Has anybody taken any kind of optimization course? Have you seen any optimization before in life?
Yeah, we're getting some hands. Yeah.
Some hands. Okay,
I mean, I know a lot of students do RL, which is a kind of optimization.
Okay, if I say the word like Lagrange multiplier,
okay,
that's the term people know. Okay, if I say gradient, I assume everybody knows what I mean. If I say Hessian, does everybody know what I mean? If I say I don't know, how about critical cone? Anybody know what I mean? Tangent cone? Any kind of cone? Normal cone? No, okay. All right, so we're going to see a few of these things. If I say KKT conditions, do people know what I mean? Okay, so we'll see how some of these things interact. This is going to be very fast and loose then, but I'll try to give you the intuition. Basically, a lot of these concepts that may sound a bit theoretical, critical cone, for example, these things are actually quite related to how, the design of effective solvers and, diagnosing problems with solvers. So, if you've ever tried to use some off-the-shelf solver like IPOpt or something, and it chokes, if it choked, there's a good reason it had to do with one of those things I just said. So that's why we should care about it. Anyway, so let's jump in. Constrained optimization. Great. Okay, so what we're going to do is just think about a really simple problem, just general standard form. We're going to try to minimize a function. Decision variable will be living in Rn. Function's going to be j of z. So j's takes in an n-dimensional vector, spits out a scalar. We're trying to minimize it because we're engineers, we minimize things. And it's subject to some constraints. And in general, let's just talk about equalities and inequalities. Okay, so this is about the most standard form of an optimization problem you could think about. What's the example here? Example would be something like a trajectory optimization problem. If we're talking about trajectory optimization, then what we're thinking is that Z here is basically like the collected states over some interval of time and control inputs over some interval of time. We're thinking that G is like a vectorized stacked version of the dynamics constraints, something like this. We're thinking that maybe like the cost here, J, is maybe like a sum over time of some stage cost. Maybe H is encoding something like collision avoidance, maybe actuator limits. All kinds of stuff. So you can kind of pretty easily map this general form to, pretty much whatever problem you care about. And anyway, after you do that, as soon as you see one of these things, if you take a course on optimization, what's going to become your knee-jerk reaction will be to do basically two things. The first knee-jerk reaction you'll have is to write out a Lagrangian. So what you'll do is you'll introduce a multiplier. Let's introduce one for, we'll call it lambda for that constraint, and maybe mu for this constraint. And we'll just write down the Lagrangian. Okay, and if you do this, maybe we'll call it script L just because that seems to be what people use. It's a function of the primal variable, this guy. And these guys are the dual variables. So Lagrangian depends on both of them, and it's just the original objective minus multiplier times constraint minus other multiplier times constraint. Okay? Sort of standard form of Lagrangian. You open any textbook, and this is what you see. The next kind of knee-jerk reaction you'll have is after you write down the Lagrangian, you'll write up the optimality conditions and pretty much start with the first order, and you'd write out the KKT conditions. Okay, and if you write out the KKT conditions, there's just a few of them, and they end up, basically just always being you take the gradients of the Lagrangian with respect to the primal variable and evaluate it at an optimal point, and it should be 0. Okay, so this is like if you're thinking of an unconstrained problem and you're setting the gradient of the objective to 0, this is the analog of that, but in the constrained case. Okay, and then there's another thing you need. Well, you need the equality constraint to hold. For sure, that should be true. And then you need the inequality constraint to hold. for sure. And you need to, here's the more interesting. So everything so far is, not so different from unconstrained case plus enforcing the constraints, but here's the kind of more subtle piece, and I'll write it and then explain. So what's going on here is we need to basically constrain the multiplier for the inequality constraint to be non-negative, and you need the inequality constraint itself to be orthogonal to the multiplier. And let's not get into why this is true. I mean, I would love to talk about why this is true, but we're going to end up blowing the entire lecture trying to explain this. So if you haven't seen this before, you can just take it on faith for now. But if you haven't seen it, it's worth learning. So anyway, what does this symbol, by the way, mean? This thing here? It's just the thing in the middle is just saying it's perpendicular, which means, if you think about perpendicular, what does this really mean? This is just saying that that should be a Z star transpose mu star is 0. Okay, so all right, so basically these are the kind of standard first order optimality conditions. And in order, so basically these are your knee-jerk reactions. If you've got any exposure to optimization, you stare at one of these problems, you immediately write down the Lagrangian, and then you immediately write down the KKT conditions. And then you stare at them and think, maybe there's something useful here. Okay, so before we talk about maybe what's useful and getting to algorithm design, what I want to do is say a couple kind of side notes. So the first thing, side note number 1, is these are not always the correct optimality conditions. So often, if you just have a very brief exposure to optimization, you are led to believe that, well, every optimization problem ever has first order optimality conditions, and these are them. That's actually false. So if you open a decent optimization textbook, what it'll tell you is that there are these things called constraint qualifications that need to hold. They're basically conditions under which these things I've written down are the correct necessary conditions. So the side note here is, I guess side note number 1 is you need to check some kind of constraint qualification. So for the folks, I think I saw one hand on Zoom for somebody who'd taken a convex optimization course. So if you've taken it or if you've kind of have friends who have, you may have heard the term Slater's condition come up. That would be a constraint qualification. A much more common one outside the convex optimization world that you would encounter would be the linear independence constraint qualification. There are a bunch of other ones too, but they're basically all just sets of conditions under which these things are necessary for a point to be optimal, for a point to solve this problem. Okay. So you got to check constraint qualifications, and if your solver that will end up describing how to solve these problems, if a solver ends up choking, it's a decent bet that a constraint qualification may be violated. So that's something to be aware of. Another side note would be that these are just first order. If you look at all the stuff going on here, think about the derivatives I need to take. There's only one derivative that's going on. I'm only taking a first derivative. So that's why we call these first order conditions. And those are not enough to say for sure I'm at an optimum. I need to definitely talk about second order conditions. I need to talk about curvature. So you should definitely be aware and check second order conditions. So that's just a couple of quick side notes. Okay.
David,
So yes.
I have a question. So in practice, when you are going about solving a problem like this, is the practical pipeline that you follow to first just write down this problem in a way that's amenable to your solver, try to crank through it. If it's choking, as you said, you then think hard about these two conditions, like the constraint qualification and the second order conditions, or do you first think about these side notes and then write it down into your solver?
I do it kind of in the way I explained it. So I always start by writing down the Lagrangian, write down the KKT conditions, and then see if there's any, sometimes there's like nice structure in the KKT conditions that tells me what, what's going on. But often it's not, often basically that just tells me how to communicate things to a solver. And actually, by the way, I should say a lot of solvers don't require you to write down the KKT conditions. So the reason I'm going into this detail is because when you're talking about solving games, you do need this. So that's why we're going into this level of detail. But if all you care about is just some, for example, trajectory optimization problem, you can pretty much just plug in this thing into your favorite solver and rock and roll. And now it may choke. If it chokes, then yeah, I would totally start writing this stuff down and see, oh shoot, linear independence constraint qualification is violated at this point. Can I find any other constraint qualification that holds there? Oops, like I'm not seeing it, so something funky is happening here. Let me see if I can massage my problem a little bit, for example.
Nice.
Yeah. Cool. I would also say there's like some small amount of subtlety in second order conditions, but let me not get too sidetracked here. Yeah, anyway, cool. I can also explain these like constraint qualifications in some more geometric detail if there's interest after the lecture. But there's like a very nice geometric interpretation of what they mean. All right. So we went into all that discussion just to like write out KKT conditions because we're going to be doing it a lot. And the reason we're doing it a lot is because as soon as we write down a game, I'm going to show you that actually, well, it's basically a different class of problem. And the way to understand why it's different boils down to staring at KKT conditions. So let me show you that. Okay, so now we're just going to write down like an n player version of the previous problem. So there's n players, and player I wants to solve this problem. He's going to minimize, choose a vector zi in Rni, some function of all the players' inputs. Okay, it'll be subject to some arbitrary equality and inequality constraints. Let me just, for shorthand, call all of this Z. Okay, so what did I do? Basically, now every player has a decision. The ith player's decision is Zi. It lives in some vector space. And there's, again, these constraints, but something important to notice is that the feasible set for player I, basically what, when these constraints are satisfied for Zi, depends upon the values of the other variables in the problem, right? So basically, player I's feasible set is itself a function of of all the other players. Okay. Okay. And that's why I put the generalized thing up at the top. If that wasn't true, if it was just some set that didn't depend, if these constraints didn't depend on the other player's variables, you wouldn't call it a generalized Nash game. It'd just be a Nash game. So anyway, that's why I put that there. Let me show you why this is a different problem, first of all. I think that's the first important thing to establish. Lasse may have talked about this a bit last week, I'm not sure, but I think this is kind of interesting. So why is this a different problem? Okay, so let's just look at a really simple example where there are no constraints. You can even see it in that case. So suppose there are no constraints. And let's say that there's just two players. You can even still see it here. So in this case, what's happening is, sorry, Z1, J1, Z1, Z2. And I'm just going to write down the second player's problem as well. Okay, if you stare at this and you write down the Lagrangian for each player is just its cost because there are no constraints. Okay, so that's easy. Let's not bother writing it down. Let's write down the KKT conditions. Again, the KKT conditions are going to be really dirt simple because there are no constraints, but here they are. The KKT conditions are as follows. Take the gradient with respect to Z1 of J1. And that has to be 0 at this point, at a solution. And the same thing, kind of pattern matching, needs to be true for player 2. Okay. So those are the KKT conditions. And let me go ahead and write, let's call this object here some function f of z. Okay. So if I'm trying to understand whether or not the problem I'm staring at is an instance of an optimization problem like the one we saw, a few minutes ago, how can I think about it? Like in terms of what I've already written down. Does anybody have any thoughts? So let me tell you why I'm asking this. So if you could prove that every game of this type was just another optimization problem, then there would be no need to study game theory ever. All we would do is just stare at one of these problems, massage it, and go and ask our favorite solver like IPOpt, and it would solve the problem, and we'd be done, and I could go home. So obviously that is not true. Otherwise, yeah, I would be going home. But why? And I claim you can see it pretty much straight away. There's like one more step that I would do. But so look at the thing in blue. Okay, look at this. I'm basically saying there's a function f of z, big F of z, that's equal to 0. And that's basically just I've stacked both players' optimality condition. Okay. That looks a lot like the kind of setting a gradient of an objective equal to 0 in an unconstrained optimization problem. So if this were an optimization problem, yeah, sorry.
So is it referring to in the game theory setting, we have like multiple objectives for different players. So you cannot just like optimize it for a single function.
But why can't I? I mean, I have a single function here, f of z.
Like Z1 and Z2, they can be like correlated like one player can affect the other one, so the actually the intuition that they're intertwined.
Sure, let me play devil's advocate just to push a little bit. So something you'll see some people that are a bit naive to is like they'll just add up players' objectives. And they'll say, look, I'm gonna look for a solution which minimizes the average cost among all the players. Like that's certainly something you can do, but it turns into an optimization problem. But it's not like, is it the same thing or is it somehow changing the problem? And anyway, I don't know if that's a good example or not, but my question is basically why can't, like mathematically speaking, why is this different? Why is f of z equals 0 different from an optimality condition of an optimization problem? Okay, let me skip to the answer. So basically, there would be an equivalent optimization problem if I could prove to you that this thing was the gradient of something. Like, i.e., if there's a function that I can take gradient with respect to z and get f. If that was true, then that problem would be the optimization problem I'm really solving. Okay, so basically what I need to do is to prove to you that this thing is not a gradient. Obviously, it's composed of gradients, but it itself is not the gradients of something. How can I prove that to you? How do you, so this is just some vector valued function. Do you know how you would argue that a vector valued, like a vector field is or is not the gradient of something? Like when I first encountered this, I had to think back to like my freshman physics class, like talking about gravity and stuff. Nobody took physics? Okay, think about gravity. Clearly, gravity, it's a force. Okay. There's also like potential energy. So like if I'm, up here, and I drop my pen, it'll fall. And so it had potential energy and it feels a force, and the force is the gradient of the potential field. Okay. And the reason, and sort of the way that I can kind of understand like the vector field that's gravity pointing down is I can understand that if I take any 2 points in space and I connect them with a bunch of different any arbitrary continuous paths, and I compute a line integral of the vector field along the path from point A to point B, like no matter which path I get, I better get the same answer. This has to be the change in potential energy. Okay. And the same, that's a general fact about integrating, taking line integrals of vector fields. Okay, nothing special about gravity. So basically that's like a way to understand whether the vector field you're looking at is the gradient of something. If you can connect any 2 points with any arbitrary paths, and for the same set of points, any arbitrary paths, you get the same line integral. That's a bit hairy to check that condition, obviously. So as with many things in calculus, there's a differential version. That was the integral condition. There's a differential condition. And the differential condition is going to look super obvious when I write it down. Okay? So let me write it down. So if I take the gradient of f, or Jacobian of f, rather, with respect to z, I get this thing. right? That's how you take Jacobians, nothing fancy. And if this was the Jacobian of a gradient, it would be symmetric because mixed partials commute. Like, right? If I take like derivative of some function with respect to variable 1 and in respect to variable 2, I could have taken the derivatives in the opposite order and I would have got the same answer. Okay, so equivalence of mixed partials tells you that this thing should be symmetric if there was a function j tilde that f was its gradient. But this thing is not symmetric. Right, and that's because of these terms. Those are different. Okay. All right, so sorry, that was a long aside, but here's the punchline. We're basically, so these games, they're not optimization problems in general. You generally cannot find some potential function or whatever that yields, whose KKT conditions basically are the right thing. So we need to actually be staring at the KKT conditions for each player individually and reasoning about those. So that's the point. So we must reason about all players' KKT conditions together, no shortcuts. Okay, so I'm not going to bother rewriting all the KKT conditions again because it's not so bad. But now we have all the fundamentals, we have all the correct language, and now we can talk about the inverse problem. So let's talk about that. Okay, so basically, we just talked about games. If we're talking about inverting games, what we're really saying is, hey, there's something about the game that I do not know. Like some third party, do not know, for example, what a player's objective is or what some constraint is or something like that. There's something about the game I don't know. And I would like to figure out what it is. Okay, so maybe I've seen some data, like I've seen players drive on the highway. I know they're playing some game deciding how they're going to drive. And I'd like to take my GPS readings from their cars or whatever, or LiDAR hits or whatever, and back out what I think they were trying to do or what constraints they were trying to satisfy. So here it is. So we're going to suppose that all these quantities, all these functions are parameterized. Sorry, was there something? We'll say that they're parameterized by something, let's just say theta is in like RP, okay? And we observe, let's just say y that's distributed according to a known distribution that's dependent on z. All right. So if this is the model, then there's lots of things I could look for, but maybe like the most, I don't know, like the dumbest thing I can start to look for is just like an MLE or something. I mean, let's start there. So I can just try to do something that maximizes likelihood. Okay. Okay. So like in notionally speaking, this is the kind of thing I could try to do. And let me just go ahead and write these things out just so we see what we're talking about. So for player I, what this looks like would be take the gradient with respect to its variable of its Lagrangian. And it should be 0. The equality constraint should be satisfied. And then the inequality should be complementary to its multiplier. Okay. So that's basically what we're talking about. And we're stacking these for all the players. Yeah.
Oh, so
Maybe go ahead.
Okay, so at the beginning we said like JI, GI, HI is parameterized by theta. Is this
Mhm.
so we're only trying to solve the parameters for one player, or does this theta parameterize J, G, and H for all like n players?
For all players.
Okay.
So like you could break this up however you want. You could say there's a separate parameter for every player. It doesn't really matter.
I guess my question was, is it obvious that satisfying the KKT conditions for each player solves the minimization problem, like the joint minimization problem that you wrote originally, or like there's still some work
So
there?
subject to the caveats here, then yes.
Okay, but that's okay. Is that obvious immediately? Just like that's like the KKT conditions of that minimization problem, or it's like there's still some connection.
Oh yeah, I did not explain what a Nash equilibrium was. I should have said, so I assumed that was covered in the last lecture. I assume Lasse talked about Nash equilibria, right?
Yeah,
Okay,
he did
so maybe quick review. Basically, if we're talking about Nash equilibria, every player is unilaterally, so fixing other players' variables, they are operating at a minimum. So how do you know if you're at a minimum? You check your KKT conditions and the
Got it.
second order conditions too. So that's basically
Okay.
why I'm doing that.
Okay. So it's by definition
Sure.
of the Nash
I mean,
equilibrium, like that's
yeah, I mean, when you look up in a textbook, what is a Nash equilibrium? They won't be writing down KKT conditions. They'll be saying, well, if I change my strategy, I do worse.
okay.
So that's how it'll be written down. But then if you're further assuming that your function is differentiable and you're not worrying about second order conditions for a minute, then yeah, that'll be equivalent to the KKT conditions. Does that make sense?
Yeah, thanks.
Awesome. Good question. I should also maybe, while I'm here, let me like make sure I'm not sweeping anything under the rug. So I'm definitely like, there are definitely very valid questions about like locality of solutions. So basically like I've just been talking about things based on first and maybe second derivatives if we're talking about this stuff. So I haven't, like there's nothing, like the most that I'm able to say based on that is that locally speaking in a neighborhood of a solution point, it's the best point. I can't make any statement about satisfying kind of global optimality properties, right? But that's also true as soon as you try to solve any nonlinear program. So that's kind of why I'm not worried about it. Right, like as soon as you open up IP ops, that's what you're doing. Okay, so here's the inverse problem. What I want to do before talking about solving it is just try to dig in a little bit to these constraints first and see like what kind of problem is this? Like, for example, here's a very legitimate question that actually the first time I started writing this stuff down like a couple years ago, it was actually with Lasse, and Lasse asked me this great question. He's like, hey, seems like if everything was like linear dynamics, like all the constraints were linear, all the objectives were quadratic, then, might there be some like convexity to this problem? And if there was convexity, wouldn't that be really nice? Like all this KKT conditions that we're thinking about, they'd be, also sufficient for global optimality for every player. Like, wouldn't that be great? So we kind of started thinking about this, and I kind of stared at it for a little bit, and eventually realized, no, actually, even in that very restricted, like idealized case, this problem is not convex, and here's why. So here, suppose that we're in like the dumbest, simplest problem you can think of. Here's J. The ith player's cost is just this thing. Okay, so it's just some, oh, sorry, that's not what that's what I meant. Okay, basically Q I is just some like positive definite matrix, just some constant. Theta is just a real number. Okay, so this is like just player I has some quadratic cost that's independent of every other player's objective. What can go wrong? No constraints. Well, in this case, let's just kind of stare at this condition. There's no constraints, so basically the Lagrangian is ridiculously simple, just the objective. So if I take the gradient of the Lagrangian with respect to Zi for player I just get this. Okay, and I need it to be equal to 0. Well, I'm multiplying theta qi zi. Zi is a vector. Qi is a constant matrix, and theta is a scalar. Here's the problem. The problem is that in this problem in this inverse thing up here, theta and z are both decision variables. Like these are both things I don't know, and I'm multiplying them here. This is basically just some bilinear expression. Okay. So, and I'm enforcing it, by the way, with equality. There's some equation where there's a product of two variables, two decision variables on the left, and it's equal to 0. Like, can anybody tell me what's the problem? Like, why should that make me a little bit scared? The one person who took convex?
You can always set 1 to 0, and then it's bad.
Okay, can you give me a better reason?
Maybe it's too unspecified then. If you can always set 1 to 0.
What was the name of the course?
Convex. I mean, it's not convex.
There we go.
constraint, and
Yeah,
that's
it's
bad.
not a convex constraint. Okay, thanks for bearing with me. So it's not a convex constraint. And the reason for this is, basically we're talking about some equation. Okay, so like some function of variables equals 0. And unless that function, is very poor, basically what that's going to define is it's going to define like a, kind of some surface in the space of all the decision variables. So it's going to basically say if we're on some surface, we're feasible. So like, let's just think about what that would look like. So like, here's z, here's theta. Let's just pretend they're both scalars. We're taking the product and saying that it's equal to 0. I mean, basically, it's something like this. Like one of them is 0, the other one can be anything. So we're kind of like anything on the axes is going to be okay. Anything off the axes is going to be bad. But like even if it was equal to 1 or something, like if it was equal to 1, you'd have something like this. Regardless, like there's so many problems with all of this. The first problem is like let's say I take 2 points that are feasible. Both of those points are feasible. The product is 0. And I connect them with a line. That line, points on that line are not feasible. That tells me that the feasible set, this blue thing, is not a convex set. That tells me that something about my problem, even though it started as this beautiful quadratic minimization, the inverse problem is not pretty. And then the second thing is also what you said, is that basically one of these things, either theta or z, has to be 0. This actually is exactly like a complementarity constraint, and those are like notoriously tricky to handle. So basically, the reason they're so hard is that there's this, basically point where things get crazy at the origin. And that will, by the way, violate some constraint qualifications. So anyway, the point is, there's things about this constraint that look so benign. I mean, it looks like all I'm doing is taking the gradient of some function and setting it equal to 0. But that can actually hide some bad stuff. Okay. All right. So basically, this is not a convex problem. What is it? It's called an MPEC. This is an MPEC. What's an MPEC? It's just a stupid acronym that means mathematical program with equilibrium constraints. Okay. Let me also give you one other quick example, and then let's talk about solvers. So let's say y is not a measurement. Let's say that y is actually a desired equilibrium. So maybe I'm like managing traffic. The z's all correspond to like density of traffic flows on particular routes. And all the drivers are being, very selfish. So it's a Nash problem. And I want the traffic flow on each route to resemble some just some setting y. Like I want the highway to be not backed up before rush hour or whatever. So then what I can do is I can write a version of this game. I can solve something like this. Okay. And basically, like all I've done is kind of subtly change the objective and my interpretation of what y was, and choose whatever norm I'm talking about here carefully. And I'm sure you can modify this further. But basically, now this problem isn't like trying to discover structure in a game that predicts observed, sensor measurements or whatever. Instead, it's more about how can I design the game? How can I offer incentives to players to change their objectives or things like that in order to influence the equilibrium they find? So it's a totally different interpretation, basically the same math.
David, is this related to mechanism design?
Yeah, this is exactly mechanism
Has
design.
anyone heard of that term, mechanism design? Yeah, it's popular in econ actually, because in a lot of econ applications, people are interested in how do you design incentives to get players, for example, like countries or companies, to operate effectively, where effectively is designed by, for example, like a regulator or something like this. And so it's a formal way of figuring out like what J's costs, right, or incentives should I design such that I get desired properties of the overall system? And even though typically it's studied in these other contexts, you could also ask the same thing about autonomous systems, right? Like, how do you design incentives for example, for autonomous car companies, or like large scale, let's say, like drone delivery systems to achieve certain desired properties. And this is one way you can operationalize that mathematically and technically churn through and actually solve for something that yields a solution to your desired property.
Yeah, exactly. So before we get into, I'm gonna even like after this one quick question, we're gonna get into I'll show you kind of two quick perspectives on how to design solvers for these. And then we'll talk about some papers. But before we do that, I want to ask, so based on what we just saw, and in particular, based on like, you know, the structure of this problem or the equivalent one before it, why is this, like, how does this differ from like a inverse reinforcement learning or inverse optimal control kind of problem?
David, are you asking specifically for this example?
Well, or like the one up here, wherever I wrote it down, this one. Like whatever, any of these problems where I'm basically trying to find parameters of a problem such that, you know, it agrees with what I measured or what I want and satisfies some optimality condition.
I'm gonna guess maybe it's because like the equilibrium constraints are just equilibrium constraints versus RL, you have like a reward maximizing constraint.
Yeah, so in either of these IRL or, you know, if you choose to minimize instead of maximize IOC sort of problems, what you're doing is you're focusing on a single player. And you're saying, okay, like I'm watching this guy. He's doing something or they're doing something. Let me try to figure out what they could be, you know, maxing or minning that would yield this behavior. But in this problem that we're staring at here, or the one on the previous screen, those equilibrium conditions are coupling all the players together. So basically each player's objective depends upon the other player's variables, and same for constraints. So you can't just like tear them apart. If you tear them apart, like they're just terms that you don't like, that you're just ignoring. So if you did this in a multi-agent case where there was actually like non-trivial amount of coupling between players, then, you know, if you were to just stare at one player, you wouldn't be able to understand why are they, you know, why is this car slowing down? Why is this car speeding up? Well, because it depends on what the other guy's doing.
David, have you guys tried to compare a naive IRL IOC approach to doing reward inference versus a game theoretic one, and seeing if you do rollouts or predictions based on this like naive decoupled model versus like highly coupled model? Is it like globally really good? Does it only matter in certain critical points?
So I haven't done that, but I have a good friend who has, and I'll show that paper in just a minute. Yeah. It's Nagar, by the way.
Oh, yeah.
Yeah.
Cool.
Yeah.
So it seems like the underlying assumption is that like when we get like a demonstration of Y, that you're assuming that this is following some Nash equilibrium. But like, and that's why we can use the KKT conditions to like solve for the parameters. But like, if there's some structure to the problem that it's reasonable to assume that like it's not a Nash equilibrium, are there like different conditions that we can impose to like solve like an equilibrium, say like a Stackelberg game?
That's a great question, and you're totally spot on. So if you have reason to believe that the behavior you're watching is not Nash, but it's something else, you can totally enforce those conditions in the bottom, right? And so I'll show you some examples of like slight modifications. So you mentioned Stackelberg. I think I don't have an example where anybody's done this for Stackelberg, at least that I don't have it queued up on my iPad, but I will show you like a feedback Nash version of this instead of just this kind of static problem. I think I'll also show you an example that's kind of like a maximum entropy interpretation. So it's like a quantum response equilibrium. That's a different, slightly different concept. So there, you can kind of play with this a bit. Okay. All right. So let's talk through a couple quick trends in solver design. And then I want to, so probably spend 5 or 10 minutes on this and then just kind of quick show a few papers and take more questions. So there's a bunch of different kind of ideas to design good solvers, and people have been thinking about solvers for kind of some of these class of problems for a very long time. So I'm not going to be able to like really go into detail. And what I'll do also is just flash this book. If anybody's really interested in this, check out volume 2 of this. Volume 2 is in my lab for some reason instead of my office.
Can you say the title because you're a little small on our screen?
Okay, the title is Finite Dimensional Variational Inequalities and Complementarity Problems. The authors are Francisco Ficini and Zhongxi Peng.
Thank you, David. You can also text me the title and I can share it.
For sure. It's a great read. Go to a beer garden or something. It's good. So anyway, I seriously can recommend. So, but anyway, it's 2 volumes. Volume 1 is basically the theory. Volume 2 is the algorithms, and volume 2 is, yeah, I mean, if you want to learn more about how to solve these problems, look there. But that is not so much about the inverse problem. That's more about the forward problems. So what I'm going to do is kind of show you a couple quick ideas on the inverse problem, and you can kind of, we can talk from there. So 2 quick ideas. Let's think first about the simple case where there's no inequality constraints in any of the players' problems. Okay. So basically what this means is there's no inequalities and therefore no complementarity. When you write out the KKT conditions, you don't have to worry about this complementarity business. So if you do that, then the inverse problem looks like this. Let's go back to kind of maximum likelihood view. Okay. So basically, there's just equality constraints, no weird complementarity stuff. These constraints are smooth. And depending on what P looks like, assuming it's nothing crazy, like let's just say it's kind of a Gaussian noise model and you do kind of take log of it and you end up with like least squares or something, then basically this whole thing is something that you can solve with like sequential quadratic programming. Okay, so basically you can just open up sorry, let me go over here. You can open up your copy of No Spell and Write and flip to chapter 18 and just implement the algorithms. So it's basically bread and butter at that point. So that's nice. That was the first thing I did, for example, to solve these kinds of problems. Just forget about inequality constraints, blindfold yourself, and quote chapter 18. So that's not so bad. But that's also like a pretty simple case because these inequality constraints are important. I mean, they encode things like in the trajectory cases, they encode collision avoidance. Like I would never ever get in an autonomous car that didn't enforce inequality constraints. Like then there'd be some chance that it's just going to plow into somebody. So, all right. So then how do we handle inequalities? Well, there's lots of things you can do. Basically, what I'm going to show you is just one kind of quick trick you can do is you can look back at these conditions. Let me kind of just duplicate these, look down here and add, you also have this thing that looks like this. Okay, these are the constraints that you're now looking at for all players? Well, what you can do is add a solution point. So like, let's say that you've solved the forward problem. You read volume 2 of Ficini and Pang, and you solved it. Then add a solution. You know, you can just check. Like which side of this is active. What I mean is you can just check, like, for the jth entry of the constraint hi, you can just check, like, is h 0 or is mu 0? Like, one of them is going to be 0. And you can enforce that with equality and forget the other one. Because locally speaking, and this goes back to the stuff I didn't talk about like tangent cones and stuff, it doesn't matter. Locally, it doesn't matter. So you can just enforce the side with equality and forget the other half and resolve these things. This will resolve to something that looks like this. There will basically be some function, let me call it big G, I don't know, I'm just making up terms of that's equal to 0. There will be some other function that's equal to 0, and this will basically just be the active multipliers, basically the ones that were 0. And then you'll have the sorry, the ones that were not 0, what am I saying? And then you'll have the other ones that were 0. So anyway, you can kind of resolve all this into a system of equations that are actually equations. Stuff smooth, like differentiable things on the left equal to 0. And when you do this, you can basically now ask yourself, what is the derivative of, let's say, z, lambda, and mu with respect to theta? And you can ask yourself this and answer it via the implicit function theorem. And this basically is the same procedure if you kind of come across any like people putting like convex optimization layers inside of neural networks, for example. It's the same exact stuff. Basically, all you do is you just, well, it's also like kind of high school calculus. You basically just look at this and let's kind of just massage it. All this stuff turns into, let's call it some function f of w and theta equal to 0, where this w is like z lambda mu. Okay. Well, if I want to take d, basically dw d theta, if that's what I'm looking for. So this thing is like w. Then I can basically do it by taking df d theta and writing it as this guy. Basically take a derivative on the left and the right of this equation. Chain rule gives me this. And the other partial is here. And I just rearrange. And so, I mean, there's all kinds of potential headaches that I'm skipping, but basically you can do this kind of thing, and then you have to ask yourself like a few questions, like, well, was this like a square system here? like, was it invertible? Right, so you have to start asking yourself a bunch of subtle questions, but assuming we squint our eyes and don't think too carefully, that's basically what you do. So if you're able to get this derivative, the reason we're kind of going to all this trouble is because then now I'm able to tell how did the equilibrium W change when I changed theta, and I can just basically do gradient descent. Now I can basically compute dp d theta this way. And you can just solve it with gradient descent. Okay, so anyway, there's all kinds of other ways to solve this. I'm skipping like a bunch of fun and like higher performance things that you could probably do. But let me just close by kind of just changing screen here and just show you, I want to show you a couple papers, just the top of them that have done these kinds of tricks, just so you kind of have a sense of some recent literature. The first one I want to start with is the thing that Andrea asked about, which is, and also there was another question about this. So like the two questions being, has anybody compared this kind of inverse problem, inverse game to like single agent inverse reinforcement learning and just kind of done an analysis of how they relatively perform? This paper does that. There was also a question about, can you do things besides Nash under the hood? This paper also does a version of that with it's kind of noisy rationality model. So highly recommend checking out this paper. Let's see another one. This is a paper I can't recommend as highly because I'm an author, but it's but what we did here is we basically looked at kind of a trajectory game version of what we've just seen and looked for feedback Nash equilibria instead of this kind of standard static generalized Nash that we had in this lecture. So it's I don't know, Lasse probably got into that subtlety a little bit, but
Yeah, really quick. So do you guys remember the difference between like an open loop game versus a feedback game? Like in one of them, you're getting a trajectory, and the other one, you're getting a policy. So everything we talked about today, you're getting trajectories, open loop. But here, they're focusing on like the policy, the feedback version.
Yeah. So it's a different equilibrium concept, therefore it has different KKT conditions, and we just enforced those, some approximate version of those. Here's another recent paper where, basically, again, solving an inverse problem, but instead of looking for a MLE, we look for something a bit smarter. This one's basically trying to do like full Bayesian inference on some kind of vector valued parameter. But because Bayes' rule is gross in that setting, we did like a variational version. So you can kind of, anyway, check that paper out. This is a paper that kind of was the first one where we developed this like differentiable game solver stuff. It's not solving an inverse problem, but it is like making use of that kind of implicit function theorem trick.
Can you explain to the audience really quick what mixed strategies are at an extremely high level?
Oh yeah, mixed strategy is just like, let's say we're playing rock, paper, scissors. You wouldn't want to commit to a deterministic choice of rock, paper, or scissors. Like imagine those are your three trajectory options. What you'd want to do is flip a coin and with some probability, choose the option. So a mixed strategy is just encoding that randomness.
Yeah, so mixed strategies give you a probabilistic map from like state to action versus a deterministic map.
Yeah. So then this is just that exact like MLE stuff that I was writing down earlier. That's this. Oh, and then this was a fun one that I had almost forgotten about this paper and then pulled it up right before talking today. But basically this paper, we were just like, can you do like, what does this do in a SLAM problem? So like, let's say that you're getting LiDAR hits off of a bunch of cars on a highway and fixed landmarks. But you know that the other drivers are like, you're playing a game with them. You're trying to avoid collision and make forward progress and whatever else. Can like that extra knowledge help? And well, what is that extra knowledge? It's basically additional constraints. It's like the KKT conditions for the game are constraining the MLE. And so like if you didn't have those constraints, you just like throw it into GTSAM, it would do something, it'd spit out an answer, that'd be the MLE. But because you're adding these additional constraints, you basically get more bang for your buck out of the data. So we get, better performance, better like SNR. What else? Yeah, I think that's all I brought up, but let me flip back to here, and I don't know if we're out of time, but I'm done, so we can take questions.
Thank you, David.
Yeah.
I'm gonna stop recording.